Hello, and today in our final installment of the lecture, we're going to discuss the idea of reaction rate, discuss equilibrium concepts, how the two are compared, and we'll take the time to close up with a brief mention about nuclear chemistry. Now, as I've mentioned before, you're encouraged to follow along using the guided notes. And as another available tool or resource, the OpenStax textbook second edition is available for your viewing pleasure. Now, what I've done is I'll go through the presentation of things, and if there is something that I recommend for extended use or extended resource, you're encouraged to go about doing so. And so let's go ahead and get started. Again, we're going to address the reaction rates. We'll talk about the rates of a reaction. We'll streamline that and discuss the idea of chemical equilibrium, which to me will tie in directly or indirectly to the principle of Le Chatelier's. And then, again, we'll close up with some nuclear chemistry. So, first things first, a chemical reaction can occur at different rates. Some reactions are fast, some are slow. And as a practice, chemists try to study and understand these rates of reaction in order to better control them and understand chemical reactions. Now, the general study of a chemical reaction's rate is known as kinetics. And if you think of the word kinetic, it comes from energy and motion if you talk about kinetic energy. So, kinetics is looking at the motion or rate of a reaction. Now, the rate of a reaction represents the change in the amount of a reactant or product per unit of time. So it's kind of a rate of how fast it reacts. And so they are always positive quantities. And so whether you're talking about forming reactant or forming product, you want to think about it in that context. And their stoichiometric factors, meaning those numbers or those coefficients from the balanced equation, actually relate to reaction rates. So it's impactful in that regard. Now, all reactions can work both ways, going in either direction. And they can go from reactants to products or products to reactants. And that's true for rate because there is a forward and a reverse reaction rate. Speaking of which, let's go ahead and define that. Your forward reaction is where your reactants are converted to your product. And then your reverse reaction is what converts the products to the reactants. Now, the cool thing about that is when you start thinking about reactions that can occur both in a forward and a reverse direction, it's almost like you need more than just one arrow to go in one direction. So keep that in mind as we proceed further and talk more about the reactions. In the example provided, it's showing you how in one case you have NH2 reacted with the 3H2 and it yields 2H3. Well, really ammonia, sorry. And then that's the synthesis of ammonia. And in the reverse direction, you can see how the reverse the reaction and it goes in a different complete trajectory where the ammonia is actually decomposed into its constituent molecules. Now, there are several factors that will affect the reaction rates. One of those things that affect the rate of a reaction is the chemical nature of the reactants. Meaning, some reactants, depending on where they're located on the periodic table, will show an inclination to react more vigorously than others. So you want to be cognitive of that. Now, looking at another factor that affects the reaction rate includes the state of subdivision of the reactants, meaning their surface area. This means that if you imagine a whole peel versus a peel that's kind of chopped up and broken down into smaller pieces, you impact the surface area, and actually increasing the surface area increases the contact areas in a reaction, and so they favor increasing the rate of reaction. Now, other factors that affect include temperature, and generally speaking, temperature increases the kinetic energy and therefore increases the rate of reaction in most cases. Now, another impacting factor would be that of increasing or variations in the concentration. Now, if you increase the concentration of your reactants, you can increase the rate of your forward direction of a reaction. However, Decreasing would have an alternative effect where it would actually reduce the rate of reaction. And then lastly, you have the presence of a catalyst, which works on a chemical level to induce a reaction to perform. And we'll talk about that in a little bit more detail a little bit later. Now, when we talk about rate and collision, chemical reactions occur as a result of collisions between reactant molecules. And in terms of chemistry, you want those collisions to be considered effective collisions, because although there are several reactions that occur, there has to be the perfect orientation, perfect scenario for many of these actual reactions to take place. And in some cases, they might collide, but it may not yield a reaction. Now, the higher the concentration of reactant molecules, the more likely those molecules are to collide and react, and therefore the faster your reaction rate. Now, as reactants get consumed and you lose the amount of reactants that you have present, you get less frequent reactions, and so the reaction rate actually declines over time. So in a reaction, you want to take home the message that at the beginning of any reaction, its reaction rate is going to be the greatest in the beginning, because you're going to have the most reactants readily available for that reaction to happen. Now let's talk about collision theory. Now, reactants, i.e. atoms, molecules, ions, must collide in order to react with each other. And there are certain postulates to this idea of collision theory. And we're going back to the idea of creating effective collisions. Now, the rate of reaction is proportional to the rate of reactant collisions. So, the more collisions you have, the greater the rate of reaction. And that's not saying that every collision yields a reaction. It just says that the more collisions happen, the greater your chance of creating a reaction. Now, number 2 says that molecules must be oriented properly. That means in order for the reaction to happen, there has to be kind of a perfect alignment or array or structural arrangement so that the specific part of that molecule can specifically interact with another part of another molecule, or else the reaction will not happen. Now, thirdly, when we're talking about collision theory, the molecules must have enough energy to react. Now, if they don't have enough energy, then there's not enough energy for the collision to actually occur, and it may not yield a reaction. Because remember, when you're talking about these reactions, there's a process where bonds are broken, and then those bonds have to be formed. And so there's a certain threshold that it has to overcome in order for a reaction to be successful. In many cases, we talk about kind of a threshold as being like our activation energy, or the energy needed to kind of start the reaction. Now, when molecules have kinetic energies that are really small or not strong enough, they'll just bounce off each other and nothing happens. So you have to have a perfect alignment, and they have to have enough energy, and you want there to be as many collisions as possible in order for you to create what's called an effective collision and yield a reaction. Now, as I mentioned, this term activation energy is basically the minimum energy needed to form a product during your collision of reactants. So when you're thinking about the idea of a reaction energy diagram, and I'll be showing that in a few slides, it represents kind of this curved depiction of how energy needs to be achieved in order for a reaction to occur, and kind of energy profile once the reaction occurs. And you understand better the principle that there is a certain amount of energy required to start a reaction. Now, the reactants actually form something called an intermediate, which is an activated complex. And this is kind of like a transition state. So if you were visually seeing that, it would be the point where a bond is just, starting to attach and they're just about to break. It's right there in that threshold where it's a transition state, and it's not something that can be actually quantified or measured right then and there, because it's a moment in that process. So here we are showing that graphical depiction I mentioned, and you see kind of a curvature where you start off with your reactants, and then what happens is if enough energy is achieved, they reach that hump where you have your activation energy, or activation energy is achieved, and then you achieve what's called the activated complex, where everything is kind of connected, and it's not your final product, but it's about to be your final product, because as it reacts, your bonds are being broken, your bonds are being formed, all kind of in a synergistic, almost synergistic way, where they're just kind of connected and happening all at once. And then you finally yield your products on the back end, where the energy is kind of represented at a lower threshold. And depending on the nature of what you're working with, the activation energy can actually be lowered. And so that's why in this particular graph, you see two humps. You have a hump right here, which is probably your standard activation energy. And here, from a biological standpoint, they're showing how this threshold has actually been lowered. And this is lowered by an enzyme. Now, we may have heard of enzymes, and hopefully you make the term enzyme synonymous with the word catalyst, because a catalyst actually helps to facilitate reaching that activation energy. Because if you notice, it looks like when you have your enzyme, your activation energy is lower than when it doesn't have an enzyme. And so if you're thinking about the ability of a catalyst, it is helpful in that regard. And then the other part of an enzyme, or in this case, a catalyst, excuse me, is that the catalyst is not actually a part of the reaction. It just facilitates the reaction in that capacity to reach the activation energy, but it does not participate as being part of the final products. And so essentially, it is just kind of a helper, placeholder made, if you will. And I guess if I was thinking of the analogy of probably football and being a field goal kicker, if you were kicking a field goal, they would be kind of like your placeholder, and the person kicking the field goal would be the kicker, which is the actual reactants. And the placeholder just kind of puts the football in a position for the ball to be kicked, and the catalyst, or i.e. enzyme, puts it in a position for the reaction to occur. So thus far we've talked about reaction rate, how it's impacted. We've talked about there being a potential for there being a forward and a reverse reaction. But one of the things you want to consider is the fact that because you have a forward and a reverse reaction, that means that a reaction should be possibly reversible, meaning the reaction should go in both the left and right direction. And for the most part, this is true for most reactions to some degree, even the ones that seem like they go to pretty much 100% completion. Now, when we're talking about this idea of a reaction that goes backwards and forward, we're talking about the prospect of a reaction going through chemical equilibrium. And chemical equilibrium just basically refers to a reaction going in the reverse and forward direction. And so you get that reverse indicator by the by the balanced equation featuring these double arrows depicted in the green reaction on the bottom. Now, because there is double arrows, it suggests that the reaction can go both left and right. And this is true. And what can happen in this reaction is, while they both can go left and right, it doesn't guarantee or mandate that you have equal amounts of your reactant and your product. So let me go ahead and restate that, because that's going to be an important takeaway for chemical equilibrium. And that is that even though you have this double arrow where they're going left and they're going right, it does not guarantee that you're going to have equal amounts of your reactant and your product. You might have more of your product and less of your reactant, or you might have more reactant and less of your product. Equilibrium is more of a dynamic function. That means that, like, as one is giving 3 to one way, the other is giving 2, and they've reached the status where the rate in which they're giving away things is equal, or sorry, not equal, is more of a static, more of a non-fluctuating movement. And so that's what we're thinking about when we're talking about equilibrium. Now, let's talk about this reaction initially. Well, when you start any kind of reaction, before it even reaches equilibrium, you have to start with some initial amount of something. And so if you place the first molecule in a container, you would just feature this blue molecule. This was just placed in a container first. This would be your initial. And over time, you would produce more of the brown. Now, eventually you get to a point where you have brown being formed and blue being formed between these two reactions. And so therefore, you have kind of a reaction that occurs. Now, to restate that, initially you have the forward reaction where you're just starting with this and it begins to form this, going that way. And over time, as this builds up, it starts going back and forming this. Now, when they get to a point where they're evenly, distributing stuff, meaning not necessarily at the same amount, but more like this guy is forming this guy at a consistent rate, and this guy is forming the blue forming the brown at a consistent rate. That's when you've reached equilibrium. Now, the takeaway message here is that at equilibrium, the amounts of both the reactants and the products stop changing. So your concentration of both, once they've reached equilibrium, stops fluctuating, stops changing. That doesn't mean that their rate of transition to forming one another is the same, nor does it mean you're going to have equal amounts of your reactant in your product, but it does say that they stop changing their amounts. And so let's look at this graph and understand what I mean by that. In any given reaction, you're going to start off with a certain amount of your material. Let's say this blue line represents the one you started with. You start off with your blue, and as time proceeds, you start to form red. And that's why this red line is starting to increase. Now, as that red line is increasing, the blue line is decreasing. That's because the blue line is being converted to red. Well, at some point, the red starts being converted back to blue. And so what happens is each of these reactions keep proceeding until they reach equilibrium, which represents a point in which the concentration of each of these stops fluctuating or changing. They kind of plateau out. Now, the other take home from this graph is that you should see that the blue line height and the red line height are located at different points. And that's true because that means that you might have more of the red total and less of the blue, but between the two of them, they are not changing in their concentration. So overall, there might be more red than blue, but what we're saying is that they're exchanging or going back and forth at a rate that they're just kind of not changing the amount that they have. It's just what they are. Now, here's another scenario where you are reaching equilibrium, but notice the difference where these two lines. In this case, the two lines meet, and when equilibrium is reached, the lines are met at a place where you have equal amounts of red and blue respectively. Now, that doesn't always occur because if you see here, these reactions can yield this result where you have more of the material on the product side than the material on the reactant side, typical left side. And you want to keep in mind that these reactions are going to vary depending on what you start with in terms of where they reached this equilibrium point. Now, this dotted line represents the time at which equilibrium is reached. And notice, the same thing, this one has the time where equilibrium is reached, and it's basically where the line starts to plateau out. And it constitutes both the forward and reverse direction of a reaction. Now, the rate of a forward reaction starts out fast, which I said kind of before, and you want to keep in mind that at the beginning of any reaction, that reaction rate is going to be the greatest that it's going to be. Now, the rate of a reverse reaction actually starts off slow, but speeds up as the concentration actually increases. And so once the rates of both reactions are equal, your equilibrium is established. And so now we're able to connect the idea of rate reaction and equilibrium. Your rates reach a point where they have leveled off and your concentration doesn't change. Now, when there is no further changes in your concentrations of both the left side and the right side of a reaction, then you have reached equilibrium. Now, some common equilibrium misconceptions, and this is a big one. The amount of reactants and products are ordinarily not equal to each other at equilibrium, and I've kind of harped upon this particular discussion point before. Equilibrium does not mean that you have the same amount on the left as the stuff on the right. It just means that they have both reached a concentration threshold where they're able to exchange at a rate that they're okay and comfortable and not moving. So it might be a scenario where you're forming 3 of these 2 NO2s and you're forming 2 of those N2O4s, and part of that would stem from just the fact that they've reached a pacing that is kind of a sweet spot for them. So moving to number 2's misconception topic. Although the amount of reactants and products remain constant at equilibrium, the system is not static at equilibrium, and you want to understand that chemical equilibrium is a dynamic process. And dynamic means that you can have equilibrium, and then if something is done to disrupt or affect that equilibrium, it's going to change where those 2 lines plateau out, or they'll reassert themselves to re-plateau out. And that's important because it's almost like relating to the analogy of being a person. At a certain point, you know, if you're sad, I would hope that you would try to do something to counteract you being sad. Or let's say you are happy and something is introduced that makes you sad, and then you are sad, then hopefully you'll reach a point where you're happy again. So that's kind of what we're talking about, how equilibrium is affected. Now, from a mathematical standpoint, we can look at the various thresholds of where a reaction is, both at the start, the beginning, the middle part, and this is based on something called a reaction quotient. And it gives you a mathematical expression comparing the rate of product formation to that of the reactant formation. And so if you look at this equation, it's represented by saying QC is equal to C raised to C, D raised to D, A over A raised to A, and B raised to B. Now, in this case, we're assuming that C and D represent our products, and we're assuming that A and B represent our reactants. And when we're saying that, we're saying the things on the right are what's going on the top, and the things on the left are what's going on the bottom of a reaction. Now, to kind of reiterate what I just said, you're looking at this quotient reaction, and this represents the reaction at any point in the reaction. This is not necessarily at equilibrium. This could be at the start of a reaction. This could be at the end of a reaction. This could be, 2/3 of the way of a reaction. This affords you a reaction quotient, and it just gives you kind of an eyeball picture of where a reaction is in terms of formation. Now, part of what it uses to compare this is the molar concentration of compounds. And so if you look at C, you look at D, you know your molar concentration of compounds, and then each molar concentration is raised to the value of the stoichiometric coefficient. That means it's the coefficient that's associated with that particular element. And so each of those elements have a coefficient. Notice when I'm saying coefficient, I'm talking about the number that would, in a balanced equation, precede the chemical formula, and that would be what's raised to the value here. Now, when you are using this expression, it doesn't have to necessarily be at equilibrium. It does not have to be at equilibrium. That's why it's given the constant of being called the reaction quotient. And so the reaction quotient must be expressed using molarity, which is concentration, and was covered in the previous discussion. And the products of concentration are in the numerator, and the reaction concentrations are in the denominator. So the bottom is where your reactants go, and the top is where your products go. And they're raised to the coefficients. But in order for the coefficients to work, the equation must be balanced. Now, the numeric value of QC, or the reaction quotient for a given reaction, can vary prior to equilibrium, and it depends on the concentration of both the products and the reactants that are present at that particular moment. Now, you can calculate your QC at any point of a reaction, and it may not necessarily mean that it's at equilibrium. So that's important to note when we're talking about the value of QC. Now, if we start with the reaction by mixing only reactants, your C and your D is equal to 0. And this is because you start with only reactants and no products. And eventually that changes over time. Now, the law of mass action says that when a reaction has achieved equilibrium at a given temperature, the reaction quotient always has the same value. So what does that mean? Well, the QC represents that reaction at any point in time. But when you reach a point where it has achieved equilibrium, the QC becomes a completely different value, which we call the equilibrium constant. Now, the value of Q when the reaction is at equilibrium is the QC. And the QC, the QC is not necessarily at equilibrium, but when the QC does reach equilibrium, it becomes the KC. Now, you do not want to confuse this with the kinetic rate constant, but it does help us with understanding that the equilibrium constant and the reaction quotient are only different in the sense that the equilibrium constant only represents that ratio of products over reactants at equilibrium. So let's compare them. If we're talking about the reaction that features QC versus KC, let's talk about how they're achieved. First, the approach is pretty much the same, where you calculate QC by putting the products over the reactants. That's the same when calculating the KC, products over reactants. Now, for the QC, the concentrations can be those at any point of a reaction and not necessarily just at equilibrium. However, the KC, or the equilibrium constant, is limited to only when the reaction is at equilibrium. Now, neither of these guys use units because units are not required. Now, the QC can change over the course of a reaction. And in fact, there are some take-home values from the information of a QC. If the value is 1 or greater, that means the products are favored in your reaction. Now, if the value is between 1 and 0, it's going to mean that your reactants are favored. Now, what do we mean by that? We're saying that mathematically, if you're given values of your products over your reactants to determine the reaction quotient, the QC, it will yield values that are either going to be greater than 1 or less than 1. But it's always going to be positive. Now, let's talk about the KC, which refers to our equilibrium constant, which only happens when a reaction has reached equilibrium. Again, they do not use units, and it does not change over the course of a reaction. And so the equilibrium constant is the same, it's static, it doesn't fluctuate. However, it can be impacted by temperature. And just like with QC, a value over 1 means that products are favored, and a value less than 1, but greater than 0, is going to mean that your reactants are favored. Now, just like with the QC, a KC cannot be negative. And to reiterate these rules about KC, which is the equilibrium constant, if it's very small, meaning less than 1, the mixture contains mostly reactants at equilibrium. If it's large, then the mixture contains mostly products at equilibrium. Now, if a reaction favors the products, your KC is going to be greater than 1. It'll be a larger number. It could be 10, it could be 20, it could be any of those numbers. But if we're talking about smaller number KCs, we're talking about numbers that are like 0.2 or 0.3, 0.5, 0.7. Anything below 1 would suggest that you have a small KC value where your reactants are favored. Now, a key point is that the value of the equilibrium constant does not give indication to whether a reaction rate is fast or slow. It just discusses what the equilibrium is between them and how they compare. Now, the concentration of each component in the reactant above is at equilibrium, and they give us an example where we're given a balanced chemical reaction and we have a value of each concentration of the respective participating compounds. And we're tasked with determining whether the reaction features mostly products or reactants. Now, to solve for the equilibrium constant, because this is understood to be at equilibrium, we are going to take the products over to reactants, And so therefore, for every value, we're going to put the concentration in the brackets, because that's what the brackets mean. And then we're going to raise them to their respective coefficients. So for the ammonia, NH3, it has a coefficient of 2, so it's going to be raised to a value of 2. You have your nitrogen, which has no coefficient, so that's understood to be a 1. And then you have your hydrogen, which has a coefficient of 3, which means it's raised to a value of 3. And then when you set that calculation up, where you have products over reactants, the 3 gets squared because that 3 came from the concentration of ammonia. The 2 does not change in terms of being raised to a certain exponent value, but that number comes from there. And then you have your 1 from your hydrogen, which 1 would then be raised to a value of 3. Now, since 1 is being raised to a value of 3, that just means a value of 1. And then the 1 gets multiplied by the 2 to get a value of 2. And therefore, the 3 gets squared, which means 9. And so you have 9 divided by 2. And once you take the 9 and divide that by 2, you get a value of 4.5. Now, the takeaway from this is that if you get a K or Kc value that is 1 or greater, then it means that this reaction favors your product. That means this reaction favors making more of this. Now, the reason we conclude that is because we're able to conclude that there is more of this made than the 2 of these together. And that's why you conclude that the product is favored. Now, had this number been a fraction or a decimal number, which indicates a number less than 1, it would suggest that the reactants are favored. Now, speaking of equilibrium, there are things that can actually impact equilibrium. And one of those things that I mentioned was temperature. And what happens is if you do cause something to impact the equilibrium, the reaction will do something to reassert itself. Now, according to Le Chatelier's principle, when a chemical system at equilibrium is disturbed, it returns to equilibrium by doing something to counteract whatever that disturbance is. Now, this disturbance can cause a change in Q, and the reaction will reestablish itself. Now, remember, at equilibrium, your QC is equal to your Kc, or your Q is equal to your K. We can drop the C if you want. One is your reaction quotient, the other is your equilibrium constant. And when those are equal, you have equilibrium. Now, regarding Le Chatelier and its impact, we're going to talk about how the equilibrium can be disturbed, and we'll address what it does to affect that disturbance. The first thing that can happen is you can add or remove extra reactants or products. If you add a reactant, you're going to impact the equilibrium because it changes the molar concentration, and that should affect your equilibrium. If you take or add your product, that's going to impact your concentration of that, and in turn it's going to affect your equilibrium constant. If you change the pressure, especially when you're talking about gases and the compounds are gases, this is going to have a drastic impact on your equilibrium. If you change your temperature, it is going to influence the reaction. So those are 3 of the ways that equilibrium can be impacted. Now, let's talk about how that happens. First, if you add or remove a reactant or product. If a chemical equilibrium is disturbed by adding a reactant or product, the system will proceed in a direction that consumes part of the added species. Now, if a chemical equilibrium is disturbed by removing a reactant or product, the system is going to proceed in a direction that restores part of the removed species. So basically, if you add something to either the reactants or the product side, then that's going to stifle the ability to create on the other side. That's going to increase the rate of production of the stuff on the other side. If you add something, it's going to limit the amount of whatever that is that's being created, and it's going to induce you to create more of your products or whatever. Now, in the case of removing stuff, if you remove something, then the system will do something to restore whatever you took away. So if you take away your products, the reaction is going to do more to create more product. If you take away your reactant, the reaction is going to do more to replace that reactant. Now, the system responds in that way to reestablish or restore equilibrium and therefore make Q or QC equal to K or KC again. Now, if you add or remove a pure liquid or solid, guess what? It has no impact on the system. So it's important that you pay attention to the states of matter, because the only states of matter that probably will impact equilibrium will be if it's aqueous or if it's a gas. If it's liquid or solid, you're not going to have an impact, and it's going to have no bearing in a calculation. In fact, you won't even set it up as part of the equilibrium constant expression. So, pure liquids and solids don't appear in equilibrium expressions. Now, change in pressure of a system at equilibrium will affect the position of equilibrium when only gases are involved. This means that if you have a reaction and it has gases and you do something to the pressure, that's going to influence the reaction. For instance, if you have a system and you have more gases on the product side, by increasing the volume, it will favor production of more products. Whereas if you reduce that, it would have a direct converse impact. Now, if you talk about pressure, well, pressure is going to be one of those things where it favors the formation of less groups. And if the pressure is decreased, then it's going to favor groups where there are larger portions of a molecule. So to reiterate that, and again, to kind of understand better, I've included a link for a visual, because sometimes discussing it may not help. But when a system is compressed, the pressure momentarily increases, and this causes the reaction to proceed in a direction that decreases the total number of gases in a system. Now, when a system is expanded, the total pressure momentarily decreases, and this causes the reaction to proceed in a direction that favors the greater total number of gases. Now, if the total number of gases is the same on both sides of the equation, compression or expansion won't have any impact whatsoever. Now, if we're looking at this example here, we're saying that this has 1 and this guy has 2. So the product side favors a larger volume. It also favors lower pressure. And so if you have a system where there's lower pressure, more of this will be produced. If you increase the pressure, more of the reactant in this case would be produced. And so you want to keep that in mind. Lower number. There's an understood 1 here and an understood 2 here. And increased pressure favors a lower number. A lower pressure favors a larger number. Now, if you increase the temperature, the equilibrium is going to respond in a fashion that consumes the added heat. If you change the temperature of a system, it results in a change in the value of the equilibrium constant. Now, if a forward reaction is considered exothermic, means it gives off heat, then K decreases as the temperature increases. So it's an inverse relationship between K, or the equilibrium constant, and temperature in an exothermic reaction. Now, if you have a forward reaction that is endothermic, meaning heat's absorbed, and endothermic usually is a reaction that when you touch it, it feels cold to touch. Exothermic means that when you touch it, the reaction feels like it's hot to touch. But if it's endothermic, then the K is going to increase directly as temperature increases. So direct relationship for endothermic between K and T, and indirect relationship between the equilibrium constant and temperature for an exothermic reaction. Now, a catalyst is not going to affect an equilibrium. And I said I was going to retouch on catalysts, especially as it relates to reaction rates. And it's important because it's capable of lowering the activation energy. But for reversible reactions, the catalyst increases both the rate of the forward and the reverse reaction. And as a result, the catalyst causes the system to reach equilibrium more quickly. It's not going to affect the equilibrium concentration or the value of the equilibrium constant, but it will help them to reaching those points faster. Now we're going to switch gears and talk about nuclear chemistry, and we'll briefly talk about the types of decay. Now, from a nuclear chemistry standpoint, what's different about nuclear reactions from standard chemical reactions is that nuclear reactions are infinitesimally larger energy producing. And the idea behind this type of chemistry stems from the idea that a element can go through a sense of decay and become a whole nother element. And that's not necessarily a controlled event, because from a chemistry standpoint, the events that are capable of being controlled in the lab are generally chemical reactions where you just rearrange your atoms. In this case, you're reconfiguring a whole nother element. And so let's go ahead and address the various three types of decay and what happens in the process. In alpha decay, it undergoes a change where you have an emission of an alpha particle from the nucleus. And in that case, an alpha particle would be representative of a helium, if you will. And if you look at what happens during alpha decay, you notice that you have your mass number and your atomic number, where your mass number is located on top and your atomic number is on the bottom. And your mass number refers to your protons and your neutrons, and the bottom refers to your number of protons. Now, the proton is like the identity of the element. It's like the social security card for elements. And so if that number changes, it becomes a completely different element. And that does occur with these various types of decay when we're talking about alpha and beta decay. Now, specifically with alpha decay, you notice a decrease in not only the mass number, but also the atomic number, where it loses two of those proton particles and forms a completely different compound. Now, since protons are what are used to identify the identity of an element, that results in a transition to a completely different element. Now, when you're talking about alpha decay, notice that what changes is the proton number. Therefore, it becomes a new element. Consequently, it also changes the mass number as well. And so you want to be able to understand these conversions and how it goes from one to form another. Likewise, if we look at beta decay, it represents the emission of an electron from the nucleus. And in this particular transition, you have the gaining of a proton, and it assumes the identity of a new element, in this case, which features one additional proton. So notice the difference between alpha and beta decay. In one case, you lose two protons, and in one case, it appears that you gain a proton to form the new identity of an element. In both alpha and beta decay, the results yield a different element. Now, for gamma emission, it's observed when a nuclide is formed in an excited state and then decays to its ground state with the emission of gamma ray, a quantum of high energy electromagnetic radiation. So this has a high energy reaction and is very strong. However, it does not change the identity of the element in question. And so if you look at this particular type of decay, which is gamma decay, energy is emitted. However, the identity of the element remains intact. And here's more of a graphical representation of how those transitions occur. In your alpha decay, you notice these four are removed. And so you end up with a decrease in your atomic and mass number, with your mass number being decreased by 4 and your atomic number being decreased by 2. And when you look at beta decay, you notice that there is no transition in your mass number, but your atomic number does increase by 1. And then lastly, when you talk about gamma decay, it becomes excited in its high energy that's given off, but the identity of the element remains intact. And so effectively, we've discussed all aspects of this discussion. We've addressed the reaction rates, the factors that impact them. We've discussed equilibrium, discussed impact of equilibrium, and we culminated our discussion with Le Chatelier's principle and nuclear chemistry. And so this completes our presentation.